maybe before I start my talk, just connect to what has been discussed previously. Understanding language, there's many reasons why this is hard for AIs. One of them that has been suggested is you need to understand what the individual symbols that we use in language actually mean. And so this is the famous AI problem of symbol grounding. How do you ground symbols? One of the sort of thinking around this problem has been that you need bodies because bodies enable you to share experience. So to mean to understand what it means to, I don't know, climb a tree, you need to actually have climbed a tree. If you just manipulate symbols on the internet, essentially words connecting together, a symbol for climbing and a symbol for tree, that doesn't work. You're just, connecting words that you really don't understand what the physical experience of doing it actually means. One of the reasons I like doing what we do, which is connecting AI and robotics, is that we're giving AIs bodies for the first time, right? We're not a software that lives on the internet and manipulates symbols. And that's what drove us into the field initially, we're doing things in the real world. So we have AIs, we essentially throw them into the world, find some way to teach them to deal with the world that they need to live in and do something useful in our case, because we are a company and we need to make money. But the end, what got us into the field and what interests us is how do you ground symbols? How do you learn actions and perceptions that are actually a step towards understanding how to act in this world, not the internet. Okay, and I've brought a couple of applications of what we can do at this point with industrial robots. So most people, especially with a Berlin audience, don't really know much about production or industrial robotics. I guess that's true here. So if you just listen to the political discourse around the topic, you would assume it's a huge thing. Angela Merkel talks about the capabilities of the German national economy, and it's all about robots and AI, and we need to keep the knowledge, and we must not give the knowledge to the Chinese. And when she does that, I'm always wondering, who's she talking about? I mean, there's KUKA, they make industrial robots, and there's us, I guess, and maybe 2 or 3 more startups. She doesn't know us. But AI for industrial robotics really hasn't happened today. Industrial robotics today goes through movements that are completely predetermined. The technical word to say it is they're fully understood geometrically. So if you imagine car production, that's something we do a lot in Germany. In Ingolstadt, where Audi makes, I think, the Q2 or something, Audi knows exactly at which point in time a car is where in the factory. And when they move a robot to put a weld line in, they just synchronize the movement of the arm to the movement of the car in the factory, and both of them coincide at the same place. But there's really no coordination or sensors between those 2 elements of the system, right? So there's no perception going on with the robot to know where the car is or do anything meaningful. They just happen to be at the same place at the same time. And that works if you're Audi and can just completely control everything. And go visit the factory. It's awesome. It's a ballet of coordination, and it's super silent, super concentrated. And that's the case because they know exactly where everything is and how it will move at any given point in time. And then you move one step down to the people who make the parts of these cars, and it's not a ballet anymore. It's just machines and dudes, pushing metal between these machines, and you don't know where everything is. So as soon as you approach a type of problem in production where you need to find out where something is to do something, you're out of luck, and you typically today employ a human. So if you want to plug in a cable, for instance, the only thing traditional robotics without AI could do was the following. You get a 3D model of, so say you want to plug in the familiar lightning connector into your iPhone. The only thing you could do if you wanted to do this with a robot was you get a 3D model of the phone, you get a very expensive, very complicated 3D camera, and it gives you a point cloud about the shape of this thing. And then you fit the model into this point cloud very precisely. And then you know the 6 dimensions of orientation of this phone. And then you orient the robot the same, and you make a simple, single, linear, very primitive movements towards it. Essentially, you just orient the robot as the phone is, and then you move forward, and that's it. Right? When we humans plug in cables, that's not what we do. At no point when I have plugged in a cable in my life have I known where this thing is. I don't care. What I do is I just go towards it somehow and wiggle it and make small corrective movements as I approach. And this is precisely the capability that we give to robots with our product Mirai. So this is obviously deep learning based. So we have cameras that watch a robot make a movement. And we're doing this with a new type of robot that is easier to deploy because it's less dangerous. Traditional industrial robots are very fast, very hard, and have completely no perception whatsoever. So if you tell them to go from A to B, and between A and B you happen to be, it will kill you, literally kill you. Now, with universal robots and some new machines from KUKA and ABB, we have a new class of robots that will at least notice when it drives into you and stop, which means it's all of a sudden less dangerous to be close to them and you can actually interact with them. And one of the things you can do when you have that capability is you teach them. You show them how a good plugging in movement would look like, and that's exactly what we do when we train a robot to plug in, for instance, a cable into a phone. We grab the robot by the wrist, as you would when you teach a person to play tennis or play an instrument, and we guide the robot through the movement while our product Mirai watches with a camera or two. And then after a couple of hours of demonstrations where the robot makes the movement with the trainer and us watching, the data gets sent off to the cloud, and back comes a policy that knows how to make the right movement given any of the images that you show. And the robot can make this very complex, real-time correcting movement on its own. So before I show you an instance of this, and I will have to do a great deal of explaining of what it is that we're doing there, because production is always very special. Just the general setup of the system, you buy a robot, any robots, we don't make the robots, right? We're a software company. You buy a robot, for instance, from Universal Robots, you buy a force torque sensor, so you feel the forces on the wrist, you get a camera from us and any type of end effector. You connect all these, and there's a tablet app, and it's really simple to use. Anybody in this room could train a robot to do a very complex movement and to solve a very complex computer vision problem in production. It's really, we made it super simple to use. You connect all these, you do 2 hours of training, wait a night, try it out. Typically, you iterate this 2 or 3 times, and you're done. You have a very complex, real-time controlled, vision-driven system that knows how to find position and end effector towards a visually perceived goal. Okay, this was all the technical terms in one sentence. So we've done that. Let's maybe move over to the video so I can show you how this actually looks when you do it. So while the video starts playing, I'm going to explain to you what we're doing there. Imagine you're a factory and you make fridges, refrigerators, and you're a premium brand, so you don't want them to break. The premium brand we're working with here is Miele. What you need to do is make sure no coolant leaks out of the cooling system after production, because if some coolant leaks out after 4 weeks, the fridge will break. The way this is done today is there's like 12 soldering points on the back of a fridge where copper tubes that have been put in by humans, so nobody knows where exactly they are and how exactly they look, where copper tubes have been connected through soldering. So this is what the back of a fridge looks like, and these are the connections. We highlight them now, right? These connections, you don't know exactly where they are, you don't know exactly how they look, and some poor dude, his job is to put a sniffing probe, that's a little artificial nose, to any one of those soldering points and try to sniff if some coolant is leaking out there. Nobody wants to do this, and of course, after half an hour, they get very sloppy. So Lipa have tried to automate this for, I think, 20 years or so, and many people have failed. Now, with collaborative robots and our product Mirai, this was a matter of a week of training the robot and solving it. So what you're seeing here is a robot. So we're quite close, right? This is like this big in reality. This is a simulation of the sniffing probe. We call it den Ameisenbären. You can see why. And this is the camera that watches the scene, and this is the back of the fridge. And with a single RGB color camera, we're going through these movements. So what we did is, for each of the individual joints, we trained the robot to find it and touch it, no matter what it looks like and no matter where precisely it is. We know roughly where it is, right? There's a ball in space where it's going to be, because most of these fridges are similar when we know the model. But really, the last 2 centimeters of the movement are guided by the camera and are literally movements like we would make them when we plug in a cable or when we touch one of these things. And the cool thing is this is real time, so you can really mess with the robot as it tries to touch these things, and that's what we're doing in the next 30 seconds. Right, so this robot just tries to touch the soldering point, and now I'm just wiggling it about to show that that's all this robot wants to do at this point in time. It wants to stay there and sniff it. That's what's going on. So normally robotics people get very excited at this point because that's completely unheard of and nobody's seen it. Real-time control from cameras with a closed-loop control system is not something that anybody outside research is doing, and we've just productized it. Right now, I believe we're the only people in the world who can do it, especially as a product. And then, while we're messing with the robot anyway, I just said, okay, then let's mess with the whole fridge. That's not something that would happen in a factory, and see if it still performs and finds the goal. So that's what's happening here. Yeah, we need to wait for the video to catch up with me. Right, so robot wants to touch, and then I decide, okay, let's move that thing about, and it just does it. I think we'll see one more example of this. It moves to the right. Yes, and now I just hit it hard, and the robot, it needs to go here in this case. Right, and it just approaches, and even as we wiggle it while it moves, we go there. Okay, the rest is technical stuff and boring, so we should go back to the presentation. So this is not about sniffing fridges. The world market for the sniffing fridge application is maybe 15 installations. I mean, there's one at Liebherr-Miele, there's one at LG, there's one at Whirlpool. We're talking to all of them after we've done that. So this is not what it's about, right? This is a highly horizontal product. It's as horizontal as universal robots themselves are. What we do is we take the AI to the actual factory, record the data on site, and solve whatever the movement problem that they have there is. Right? So we're not, unlike Siri, where Amazon has trained something and deployed the result. What we're doing is we're deploying the learning system, take it to the factory, record the data there in a very specific manner to the workplace there, the lighting conditions, that there may be oil in the air and chickens running around in the background. You don't know, right? Any of these variants we learn to deal with on site. Record the data, bring it back to the cloud, create a policy, install it on the robot, and have it work. And this works for essentially anything where you need to hand-eye coordinate a movement. So the way we sell this is we go to a factory and we go to the production engineer and tell them, okay, now let's go through the factory and you show me the people you keep around where you didn't automate. The people you keep around is exclusively for their ability to coordinate how they move with what they see. Because all of this could be done with a robot instead of a person. So yeah, and this is just a technical summary of that. Here, for those of you who like to see some more videos, here are a couple of barcodes where you can see more videos where we do interesting things. This is a case where we plug in Ethernet cables. There's, I think, the first one is just the whole demo where we also show how the training process looks like. And the second one is a slightly more industrialized case where we're actually, wiring up a 19-inch patch panel where, of course, we in software know where each cable needs to go. Otherwise, we would just do random things. But then we drop off the robot in front of the right socket, and then the Mirai system, our system, does away with the variance. You can even hit the 19-inch rack while it's moving, and it will still reliably plug in. The second one you've just seen. We have a couple more of these. If you're interested, follow us. There will be more on the website quite soon. We can do this with essentially all the Universal Robots machines. There's 6 of them right now, 3 different sizes, and then slightly different equipment. If we need more speed, more power, and a bit more danger, we can also do this with ABB robots. We're in no form bound to collaborative robots. It just happens to be the case right now. The market is crazy about them and buys universal robots in large numbers. So most of the requests we get today are not for traditional ABB fast machines, but for non-dangerous universal robots machines. Two words about the company. We've been founded in 2014. We're sort of a weird animal. We're really AI people. So, the discussion about artificial general intelligence and how to make language understanding or understanding anything at all instead of just predicting stuff is really close to our heart. And it's really, long-term what I want to do in my life. And this is essentially a vehicle for me to, make some money on the side. We spent 2 years between 2014 and 2016 figuring out how doing AI in Germany makes sense, right? If you do AI and you have a bunch of good people and you have a bunch of algorithms that make sense, how do you do something where you learn something from the people around you? And it wouldn't make more sense to do this in Israel or Silicon Valley or at least in the UK. And industrial robotics or production topics are sort of a natural match for us, and that's how we ended up doing this. We're 20-ish people now in Berlin with a sales office in New York. We're venture-backed by Project A, who have invested in November last year, Coparian and Vito. So, all of these guys are very good operationally, which helps us a lot, and these guys obviously are close to just production issues and help us a lot there. That's me. I talk about robotics and AI on LinkedIn sometimes, so if you want to follow me, and I'll now be ready to take any questions you might have. Okay.
So the first questions, let's start here with Tobias.
Yes, thanks for the talk. Very interesting stuff. And since we are building sensors for robots, I also got pretty excited looking at some of those that data.
What are you working for?
Topos, I have a talk like in the one of the after the next. So so what the capability is pretty strong, and I think matching hand-eye coordination from a robot's perspective can be transferred to a lot of other things robots do. So how difficult would it be to transfer this mechanism into an autonomous driving system, for example, because that's something we're looking into.
Yeah.
So how can that help?
So the machine learning and the algorithms there are very generic. So let's not go to autonomous driving right away, but people have approached us about like harbor cranes. This is essentially a 4D movement, everything jiggles about, and placing containers into moving container ships is a high-end skill that you need highly trained operators for. The algorithms could totally do it. The company, alas, not. We need to focus at least on robotics. This is wide enough. So unfortunately, I need to say no to people who want to do harbor cranes and diggers and whatever else I have been approached about. There will be, however, a generic Cartesian interface that we add to the product, where as long as you don't tell us, you're free to try to hand or whatever your actuator is, actuator camera coordinate essentially any movement, and then if it works, good for you, that's excellent. So I believe by the end of the year we will have this generic interface with an API that you can buy one of these, you connect whatever your cameras are, and you connect whatever your machine is that you want to coordinate, and just try it and do that. Autonomous driving, I think, is different because it's more complex and layered, right? These are very monolithic skills. I think autonomous driving is typically skills and layers of skills on top of each other, interfering with each other and trying to prevent errors. In the autonomous driving space, we're strongly on Elon's side. Cameras work. This world is designed by humans for sensors that are human, which means RGB, not radar or anything else. So the most information in pretty much any case where you want to act in the world, you get from RGB data. The spectrum is there, it's usually free, nobody messes with it. So as long as you can deal with shadows and sunlight, and we're getting very close with this stuff. I mean, most of the applications we do work in direct sunlight, as long as you don't completely overdo it. So I think the visible spectrum is just the best sensor modality for anything that interacts with the world with humans in it, which is the world.
Great. Any other question? There's one.
Hi, thanks for the presentation. I'm Raphael from Siemens AG. I have a few questions. So one, if you're really using reinforcement learning to do this, and if you are, how you're handling also the transfer learning for other machines. So if you teach one machine, how can you transfer that to multiple lines, and how you're also running that locally? Are you providing your own hardware, or you're working with third-party hardware?
Yeah, a Siemens person would ask that. So is it reinforcement learning? The answer is no, not at all. There has been a great deal of excitement around reinforcement learning. The problem is for industrial use cases, you do not have the data in reinforcement learning. In reinforcement learning, you need to be able to roll out to multiple machines. So Google X did this, I think 2015 or so. They put like 20 robots in a basement and had them rehearse gripping of random objects. And what they got out of it was a mildly impressive gripping demo, and they spent 4 months and 20 robots on it. I cannot propose this to anybody making fridges, right? They buy a robot, they want to start right away. So the only way to make reinforcement learning work means simulation. So you essentially need to do some form of randomization and treat reality as some weird form of the simulation that you've trained in. I believe there's something there, but this also means you need to build the simulation first. In a production context, for many of the things that happen in factory, nobody has a simulation. Nobody has even heard of it, right? Could I have come up with this demo where we sniff copper tubes on a fridge half a year ago before I had met the Liebherr people? Hell no. I had no clue that this is going on. Has anybody, a meaningful simulation for the contact forces that are going on there? Absolutely no too. So as long as nobody figures out how to just take a snapshot of a room and get a decent physical simulation out of it, we have a strong belief that using reality as its own model is the best thing to do, and that's what we're doing here. We're recording all the data we learned from on-site at the actual thing. Transferring between different machines, you need to make sure that the variance that you see between individual workspaces has been, oh yeah, I'm over time.
No,
has been shown during training, right? If you do that, you can do it. It makes the learning more complex. The other way to do it is just make the individual working stations look exactly the same. We are bringing hardware, not out of, we have no passion for this whatsoever. It's just we need GPUs. There's no GPUs in any production context today. So we're selling this essentially, what we're doing there is we're selling a software license as a little box. The little box is essentially a gaming PC. That never updates. It brings a GPU, and that allows us to do it. I believe, once Siemens and Hewlett-Packard Enterprise and all the big guys have had their IoT wars, in a couple of years, we will know what the type of accelerated neural network inference architecture there will be in factories, and we'll be perfectly happy to run on this one. Right now, you need to buy a piece of kit and connect to your robot.